Up to this point, we spoke about torques and we spoke about forces. We said that a net torque is required to act on an object to rotate that object about some axis, and we also said that a net force is required to act on that object in order for our object to translate, to move along some axis. Now, what exactly does it mean for an object to be in static equilibrium? Whenever an object is in static equilibrium, that object is at rest. It's not moving along an axis, and it's not rotating about any axis. The object is completely stationary. So, two conditions are required for an object to be in static equilibrium. Condition number one: the net force acting on the object along any axis, along the x-axis, y-axis, and z-axis, must be zero. The sum of all the forces acting on the object along any axis must be zero. So let's look at one example in which our object will be in static equilibrium, and our job will be to use the following equations to solve for the force in the rope. So, find the tension F1 and F2 in two ropes that are connected to a third rope that holds mass M. Assume the mass M is 300 kilograms. So let's look at our diagram. So we have mass M, which is 300 kilograms, is hanging by the following vertical rope, force F3. So the tension in this rope is F3. We want to calculate what F1 is and F2, knowing that the angle that force 1 makes with respect to the x-axis, with respect to the ceiling, is 60 degrees. So let's begin by first calculating force F3. So force F3 is equal to, well, simply m times g, where m is the mass of the object, 300 kilograms, and g is our gravitational constant, 9.8 meters per second squared. So we take the product of these two values and we get that F3, force 3 in rope number 3, is equal to 2,940 newtons. Now let's move on to the following two steps. Now we want to use these two equations to solve for force 1 and force 2. Once again, we assume the object M1 is in static equilibrium. That means the net forces acting on our object along any axis is zero. So the sum of all the forces acting on the object along the y-axis is equal to, so we choose going downward to be positive and going upward to be negative. So the force that points downward is force F3. So we have force F3, which we found to be 2,940 newtons, and the other force that points upward in the negative direction along the x-axis is, well, it's the component force of force 1 that points along the y-axis. So it's F1 multiplied by sine of the angle 60. So this quantity minus F1 sine 60 is equal to 0 according to this equation. So now we rearrange and we solve for force 1, and we find that force 1 is equal to 2,940 newtons divided by sine of the angle 60, and we get approximately 6,790 newtons. Now, the same exact step should be taken with this equation. So, the sum of all the forces acting on the object along the x-axis is equal to 0. So we have one force, we choose this way, positive, so F2 is positive. We have F2 minus the x component of the F1 force, which is minus F1 cosine of the angle 60. So we solve for F2 and we see that F2 is equal to the product of this quantity and cosine of the angle 60. So cosine of the angle 60 is simply 0.5. So 0.5 multiplied by 6,790 is 3,395 newtons. So force 2 has this quantity, force 1 has this quantity, and force 3 has the following quantity. So once again, we can see how we can use these equations to solve various problems in which the object is said to be in static equilibrium. Meaning, condition number 1 holds the net forces acting on the object along any axis is always equal to 0. Now, what about condition number 2? In order for an object to be in static equilibrium, the object cannot translate and it cannot rotate. And since torque creates rotation, that means the sum of all the torques acting on the object about any axis must be 0. So the sum of the torque is equal to 0. So once again, what is our conclusion? Well, for any object to be in static equilibrium, the net torque as well as the net force acting on the object must always sum up to 0. If the net force is not 0, that means we're going to have acceleration along some axis. And if the net torque is not equal to 0, that means we're going to have angular acceleration about some axis.